Assalamualaikum. Good evening, I suppose. This is lecture 18 of CHM477, Inorganic Chemistry, the second last lecture, hopefully. Today we're going to deal with stability of complex ions. You have learned before that metals can interact with ligands in Lewis acid-base interaction, where the ligand will act as a base, donating electrons to the metal center, and the metal center acting as an acid, accepting the electrons from the ligands. Now, with that, the stability of the metal center is enhanced because anything that can occur spontaneously is increasing the stability of the product. You also know that there are monodentate ligands, bidentate ligands, and polydentate ligands. Now, monodentate ligands are the ones with one donor atom per molecule. Bidentate ligands are one with two donor atoms per molecule or per ion. And polydentate ligands are having more than three donor atoms per ligand. Now, the formation of a complex ion Ml from a metal and a ligand L in aqueous solution can be represented in the set of equations below, assuming that there are no insoluble products formed. So assuming that all M, L, and Ml, they are all in soluble form, not solid. So if you have a metal ion or a metal center reacting with a ligand L, forming the complex ion or coordination compound Ml, then by the usual treatment of stability constant, you have K1. This is reaction 1. This one is reaction 1. K1 is Ml, the concentration of Ml divided by concentration of the metal ion multiplied by the concentration of the ligand. So you get a value for K1. And then as you add more ligand into that reaction, your Ml is going to take in another ligand to produce Ml2. And on that note, K2 is Ml2, concentration of Ml2, divided by concentration of Ml times concentration of L, and so on and so forth until you reach Ml n minus 1, n is any integer, L equals to Ml n. Yeah, so your formation constant, which is your Kn, is equal to Mln, which is the concentration of this product, divided by the concentration of the two reactants. And N represents the maximum coordination number of the metal ion M for the ligand L. So there is another way of expressing the equilibrium relationship above. So you have M added with N amount of L to make MLN. So your beta N is MLN concentration divided by concentration of M and concentration of L to the power of N. Yeah? So that is the usual kinetic story where beta N is equal to K1 times K2 times K3 all the way until Kn, where K1, K2, K3, and all the way until Kn are called the stepwise formation constants, and beta n is called the overall formation constant. So you have beta n is the overall formation constant, and K1 until Kn are the stepwise formation constant. Now the magnitude or the size of beta n is proportional to the stability of the complex ion form. So the higher the value of your overall formation constant beta n, the higher the stability of the complex ion formed. So for example, if you have one cadmium, you react it with one ligand ammonia, you get that one. CdNH3 to the with a charge of 2 plus. So K1 has been investigated and found out to be 10 to the power of 2.65. Yeah. Continuing on, adding more ammonia into that equilibrium will produce cadmium to ammonia with K2 10 to the power of 2.10. And then the next step will have a K3 of 10 to the power of 1.44, and the next step will have K4 equal to 10 to the power of 0.93. So if you want to find what is the overall formation constant beta 4, so you just need to multiply K1 times K2, K3, and K4, and you are going to end up with 10 to the power of 7.12. So this is the power, this value here, 7.12, is actually mathematically simply adding up all the uh, um, exponential here. Yeah. So 0.93 plus 1.44 plus 2.1 plus 2.65 is equal to 7.12. So as ligand is added to the solution of the metal ion, Ml is going to be formed first, obviously. Yep, you can see it. Ml is formed first. And it is more predominant than any other complex in the series. And if when we add more L, Ml2 becomes predominant. It will Ml2 concentration will rise, Ml concentration will drop, and then add more ammonia, add more ligand, you get Ml3 become more dominant, add more ligand, all the way until n number of ligand. So Ml2 becomes unimportant, and so on until the highest complex, which is Mln, is formed to the nearly complete exclusion of all others at very, very high concentration of ligands. Now, a steady decrease in Ki, yeah, you can see that there is a steady decrease going from K1 to K2 becomes smaller, K3 becomes smaller, K4 becomes smaller. This steady decrease is noticed when I increases in almost all the observed cases. Yeah, although occasional exceptions can occur where Ki doesn't increase with the increasing value of I, some exceptions can occur due to steric or electronic effect. Now, generally, the magnitude of log Ki tends to decrease by about 0.5 at each step. So as you go from K1 into K2, you get a reduction of the value by about 0.5. Yeah. For statistical reasons. Yes, obviously, because of this, you have your ML going forming first, and then add more ligand. ML2 goes up, ML becomes less, and then add more ligand. So statistically, the amount of MLN that is formed is going to be a little bit slower because you still have the other species present, and usually the Ki tends to decrease by about 0.5 with each step. But that is just a general rule. So as you can see here, it is quite, this is 2.65 into 2.1. So that is a reduction of 0.5 from 2.1 to 1.4, about 0.5 as well, about 0.5 as well, a reduction with each consecutive step. Yeah, but the overall will give you a big number because you are adding up all this. Yeah, and a big number of the overall value of beta n will give you the picture of stability of the complex ion that is formed. The higher the value of beta n, the more stable that complex is. Okay, so let me go through into chelate effects. Now, chelate, as you know, chelate are ligands that can uh, bond to a metal center through more than one donor atom. So, for example, ethylene diamine being bidentate is a chelate ligand. EDTA being hexadentate or polydentate is also a chelate ligand. So as a general rule, a complex having bidentate or polydentate ligands are more stable than the equivalent complex having monodentate ligands only. You're going to see that a little bit later. That is because bidentate and polydentate ligand called chelating agents have the ability to hold metal atom like a claw. Yeah, they can hold on to the metal atom very, very strongly. They can really, really hold that metal and increase the stability of the complex that is formed. And the word claw comes from the Greek word chel, means claw, obviously. So chelation confers stability to a metal complex. So have a look at reaction 1 and reaction 2. What is reaction 1? Now reaction 1 is you have nickel with 6 water. Added to that is ammonia, 6 molar equivalent of ammonia, and all the water is going to be removed and replaced by ammonia in this way. So notice that I am always putting the arrow from the donor atom, which in this case is nitrogen, to the acceptor. So the arrow, when you are drawing dative covalent bond, and dative covalent bond is actually when you are forming a bond through donation of a lone pair of electrons from one atom to another. Yeah, so dative covalent bond is always represented by an arrow. Oh, my arrow is moving. Yeah, by an arrow. Yep. So your arrow will always have to come from your donor atom to your acceptor atom. In this case, from nitrogen to nickel. And my ammonia, which I should be writing as NH3, now I am writing it the other way around to make sure that this nitrogen and that nickel is attached through that arrow. So you have from nickel with 6 water, you have nickel now with 6 ammonia, and the beta 6 or the overall formation constant of this complex is 10 to the power of 8.6. Now 6 of the water molecules are being released when you have ammonia coming into the nickel complex. Now, we have all 6 nitrogen donor atoms in this case, and you have beta 6 equals to 10 to the power of 8.6. Now, let us compare that value with this situation here where you have also 6 nitrogen donor atoms, but these nitrogens are provided by the ethylene diamine. So this is your ethylene diamine. That's your ethylene diamine with 2 nitrogens. and the nitrogens are bonded to your nickel in this way. You can draw it in this uh, format for ethylene diamine. So nickel with 6 water reacted with 3 molecule of or 3 equivalent molecule of your ethylene diamine will make this tris ethylene diamine nickel 2 plus, and it will look like this. But what is striking here is that the beta 3 for ethylene diamine is way, way higher than the beta 6 of the ammonia complex. And the higher value of your beta 3 for this reaction 2 indicates that this complex ion, this one here that I'm circling, is a lot more stable than your hexaamine nickel 2 plus. This is a chelate ligand, yeah, chelate ligand, and this is not a chelate ligand, and you have the beta 6 becoming higher than the non-chelate. Yep. The complex with 3 chelate rings ethylene diamine is about 10 to the power of 10 times more stable than the complex with 6 monodentate ligand of ammonia. Now, there are many factors why this increased stability. I will explain to you later. Now, initially, the nickel ion is coordinated with 6 water molecules. In each of the 2 reactions, the 6 water molecules are liberated. Yep, you can see all the 6 are liberated. This one is liberated. This also are liberated. In each, the 6 are liberated when nitrogen ligands become coordinated. Yeah, as you can see in the first case, 6 ammonia. In the second case, 3 ethylene diamine that carry 6 nitrogen. In that score, the 2 reactions are equivalent. With monodentate and with bidentate, it looks like they are quite equivalent because they have from bonding to oxygen now to 6 oxygen, now they have bonding to 6 nitrogen for both. However, for reaction 1, 6 ammonia molecules lose their freedom at the same time, but for reaction 2, only 3 ethylene diamine molecules lose their freedom, and thus there is a net increase of 3 mole of individual molecule. Reaction 2 causes a much greater increase in this order than reaction 1. What does that mean? Here you have one entity, yeah, NiH2O6 plus, this is 1, and here you have 3. So in here you have 4 molecules in the left-hand side of the equation. You have 4 molecules, whereas on the right-hand side of the equation, this is the right-hand side, you have 1 molecule plus 6 molecules, so 7. So there is an increase of entropy as we look at reaction 2, from 4 molecules in the reactant to become 7 molecules on the product. But when you look at reaction 1, 7 molecules in the reactant also gives you 7 molecules in the product. So let's have a look. In reaction 1, 6 ammonia molecule loses their freedom at the same time, whereas in reaction 2, only 3 ethylene diamine molecules lose their freedom, and there is a net increase of 3 mole of individual molecule. Now, reaction 2 causes a much greater increase in this order because from 4 molecules to become 7, so you have an increase. Therefore, the delta S naught, which is the standard entropy change for reaction 2, is more positive, i.e. the reaction is more favorable. The more positive of the more the entropy is increased, the more favorable that is. Entropy means the degree of randomness. So you have from 4 to become 7, your entropy is increased, and an increase in entropy is always, always favorable. How can you understand that? Now, anything that makes a mess is very, very favorable in nature. Anything that makes a mess. Just look at your room. How easy it is to clean up your room compared to make it messy. Of course, to make it messy is a lot easier. It is more favorable to become messy because being messy is uh, entropically favored. So when you don't wonder now why it takes you big effort to put your room in order, put your pillow here, put your books there, put your pens here, take away all your mess. It takes a lot more effort to clean up than to mess it up. To mess up a room, you don't have to do anything. You just have to sit here. You just sit there and it will become messy by itself. So the answer to that is entropy. Yeah. Anything that increases entropy is favorable in nature. Anything that becomes messy is favorable. But so you have to always fight. You always have to fight the natural tendency of being messy and tidy up. My daughter is really enjoying this lecture. It is then said that this enhanced stability, called the Chelate effect, is entropy driven. Yeah, entropy favors the increase of the number of molecules. So that reaction is entropy driven. Note that all processes that increase the entropy, which is S of the universe, will be spontaneous and favorable. Now, at the same time, you can have a look at this equation, which is an equation that is very, very familiar to all chemists. Delta H naught is equal to delta E naught plus P delta V. The enthalpy, which is this one, you can see that the enthalpy, where are they? Here. Looking at this, for example, yep. Looking at this, here is cadmium reacting with 4 ammonia to make cadmium ammonia 4 2 plus. So from 5 to become 1. And here you have log beta 4 is 7.12. Enthalpy is 52.5. Entropy is negative. And then you have the second step is the second reaction is cadmium with 4 substituted ammonia, which is MENH2. You have the log beta 4 is less than this one at the top, 6.55. The delta H naught is, they are both almost the same, not too much difference. But the entropy here is more negative. Whereas the third one, when you have cadmium, when you have cadmium reacting with 2-ethylene-diamine, the log B4 is a lot higher, which means it is more stable. This one here is more stable than that one. And this one here is more stable than that one. Because, oh, sorry, I'm wrong. This one here, yep, because log B4 is 712, is more stable. Your cadmium NH34 is more stable than your cadmium methyl NH24 because the log B4 for A is bigger than the log B4 for B. So, but the log B4 for C, which is your chelate, is the highest. Yeah. So you know that this compound is more stable than that compound, and that compound in A is more stable than the compound in B. Again, you look at the enthalpy, there's not too huge a difference between A, B, and C, but your entropy, delta S naught for reaction C, is a lot more positive than A and B. So what does that mean? What do these values mean? The values mean when you look at the log B4, the values of log B4, reaction C has the biggest value, therefore chelated complex. CD ethylene diamine 2 has the highest thermodynamic stability. It has the highest thermodynamic stability. But when you look at the value of delta H naught, which is the enthalpy, all the reactions do not show very different values. Therefore, the extra stability of chelate products has, of the chelated product has over the non-chelated product is not enthalpy driven. It is entropy driven because we see that the uh, values of delta S naught, you have the CDEN2 produces the most positive entropy compared with the other two. So it is not enthalpy driven. This stability is entropy driven. Yeah, looking at the values here. So everybody knows or this reaction or this equation, Gibbs free energy is equal to minus RT ln K and equals to delta H naught minus T delta S. So can use this equation and you can get all these values calculated and you can make your conclusion that the stability is driven by what? Is it driven by enthalpy or is it driven by entropy? In the case of this series here that you see A, B, and C, the stability of CDE and 2 plus is definitely entropy driven. Entropy driven. So that is chelate. So chelated compounds are very, very stable. And most of the time, that stability is due to entropy change. Yeah, entropy driven. Because it's a lot messier. The product is more messy than the reactant. So that is very, very favorable. Right. I'm going to go into the last topic in this particular lecture, which is the macrocyclic effect. As you can see previously, I'm talking about the chelate effect. Yep. The chelate effect is when you have bidentate ligands bonding to metals, so you get a chelate. So the chelate effect increases the stability. But macrocyclic effect increases the stability even more than the chelate effect. So what is a macrocycle? A macrocycle is a ring of at least 9 atoms, of which at least 3 are donor atoms. So if you want to make a macrocycle, you have to have at least 9 atoms in this ring. Now, can you see that? Oh, excuse me. Can you see that this is a ring? Yep, that is a ring. It has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. Oh, I'm counting it wrong. We start from here. 1, excuse me. Okay. We start from here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 15. So 16, sorry, you have 16 up to here. Yeah, because we start from there. So this one is a 16-membered ring macrocycle and it has 4 nitrogen donor atoms. So this fits the definition of a macrocycle. Now, the macrocyclic effect is a name for the greater stability of complexes with macrocyclic ligands over complexes with analogous acyclic ligand. Acyclic means non-cyclic. So if you have a metal bonded in the middle here with this macrocycle, the product is extremely stable complex. Yeah. For example, if you put nickel here, you're going to have the nickel bonded to nitrogen all the way until the 4. And then there is a ring around it that is made up of more than 9 atoms. And this is going to be a very, very stable compound. It is not going to be easily decomposed. Yeah. The microcyclic effect describes a further degree of stabilization than the chelate effect. Chelate effect is making the compound more stable, but not as much stable as the macrocycles, as we can see. So the formation of zinc 2 complexes by the 2 ligands above. This one here you have a situation of, La is a non-cyclic ligand, whereas Lb is a cyclic ligand. So this is a cyclic ligand, this is non-cyclic ligand. So what happens when you study the formation constant? So when you are reacting zinc with La and Lb, here is your La and your Lb, what are the values that is obtained? So you're going to have for ZnLa2 plus, the log K is 11.25. Yeah, this is definitely a chelate. Yeah, because it has more than one donor atom. It is a chelate, but this is not a macrocycle because this ring doesn't close. This one is a macrocycle. So when you have a high value of log K, you know that that compound is very stable. But when you provide a ring closure here, that value becomes a lot higher. It goes up from 11.25 of your log K into 15.34. So you already know, looking at those values, that your ZnLb2 plus is a lot more stable than your ZnLa2 plus. The enthalpy, change of enthalpy is 44.44, the first one, and 61.9 for the second one, whereas the entropy change is going from 66.5 in ZnLa to 85.8 in ZnLb. So what can we deduce from these values? Now, the first one that you can deduce is this. The bigger value for log K for the formation of the macrocyclic ligand, which is ZnLb2 plus, shows that macrocyclic complex is more stable than the acyclic complex. This is your acyclic complex. Number 2, the more negative enthalpy value for production of ZnLb2 plus indicates that it is more thermodynamically stable than ZnLa2 plus. So this is bigger, this is smaller. So your ZnLb is thermodynamically more driven. Yeah, the stability is driven through thermodynamic. Yeah. The more energy is given off during formation, the product will have lower energy, so becomes more stable. And number 3 is the entropy of formation of ZnLb2 plus is more positive, which is more favored than your ZnLa. So these two reactions, when you compare them, you will see that the stability of this macrocyclic compound is entropically driven as well as enthalpically driven. Yep. So for the data, it can be concluded that the overall stability effect is both enthalpic and entropic in origin, driven through enthalpy and driven also through entropy. The values above also show clearly that the stability produced by the chelate effect shown by the formation of ZnLa2 plus is less than the formation of the macrocyclic ligand, and that is called the macrocyclic effects. Right. So that wraps up the chelate effect, the macrocyclic effect, as well as the stability of those two types of compounds. So I hope you understand this lecture, even though it is dealing with a lot of numbers, but it is quite easily understandable. If you're having some problem, again, you can ask me in the chat group, or you can listen again to this video, or you can go through the notes that I've provided to you. So that's it for now. Thank you very much. I'll see you in my last lecture, which is going to be lecture 19. So take care, study well, and keep safe. Assalamualaikum.